But yeah, I think this is
that's very short because like when I'm saying it must be good defined, like I don't find.
Okay, let's start. And before I start with the permutation models, I'd like to draw your attention to these two dates. Last Friday, it was the, I don't know how many, 146th anniversary of a letter that Cantor wrote to Dedekind. And what was in the letter? For some reason, he was interested in the positive integers and the positive real numbers. Okay, the German sounded way nicer, but this is the short version of the question that Cantor asked of Dedekind. Do you know if this might be true? And there were reasons why Cantor was interested in this. Dedekind apparently replied, well, that's a silly question, of sorts, but they wrote back and forth, and I looked in there's a collection of letters between Cantor and Dedekind, and the post must have been quite efficient, because one or two letters went back and forth between them, where they discovered that the rationals are countable, that the algebraic numbers are countable, because on the 7th of December, in little over a week later, Cantor wrote to Dedekind with a proof that there is no bijection between the two. So this coming Saturday, you can celebrate that event. 146 years of the uncountability of the real. There will be parties all over the country, I imagine. I will sit silently at home and celebrate all by myself. Anyway, I just wanted to let you know that you live in an important week, set theory-wise, between these two dates. And so in a few years, we can celebrate 150 years of the set theory, basically. This was the week in which set theory was born, I would say. Okay, and lots has sprouted forth from that correspondence. By the way, Dedekind thought or wrote in his diary that this was a silly question, but after Cantor gave the proof and they had realized that the algebraic numbers did form a countable set, Dedekind wrote in his diary, well, actually, that was a pretty good result, because now we know that very, very, very many of the real numbers are not algebraic. So it's a really strong existence theorem for transcendental numbers. It doesn't help deciding whether pi or e or some other number is transcendental, but it tells you that almost all the real numbers are transcendental. So he was duly impressed after all. So, what were we talking about last week? And I want to finish or talk about the Mostowski model in a bit more detail than I did last week. I kind of hurried through some of the salient facts, but I didn't talk about how all those things worked. And I want to do that. And then I'll also indicate, if time permitting, how you could prove the consistency of having atoms at all. And if you don't like atoms, I will also indicate how there's another way to make permutation models. Essentially the same, but conceptually slightly different. Now, what are the assumptions in the Mostowski model? Let's recapitulate. There is a countable infinite set of atoms. We have a linear order of those atoms in type eta, as Cantor used to call that. So isomorphic to the rationals. Okay, and we can also say the order preserving permutations of A, but we can pretend that we're mathematicians and call them the order automorphisms of A. So we look at all the order preserving bijections from A to itself. And what I was talking about last week, we use subsets of A as supports in the construction of the filter, because now the filter the filter of subgroups that we use to define symmetry, that simply derives from the ideal that we take. So these are all, this is the filter generated by all the fixed things of the elements of the ideal. So this is what we set up last week. What were the salient properties of the model? Well, they'll appear here, and we'll get through no matter how you slice it, the subgroup of G of all the elements that fix all the elements of A, that's just the identity map, and that is not that's not in the filter, definitely. So in the derived model, the symmetric model that we get from G and F and everything, there is no well order of A in that model, because that's how you can characterize the things that do have a well order in the model. Their fix group should be in the filter. Okay, and that's going to come back to haunt us in a moment, or in the homework. What's the symmetry group of that linear order? Well, the symmetry group of the linear order is just the whole group, because it preserves the order. Because if you calculate, I mean, the order is a subset of the square of A, and if you calculate what pi does to every element of that subset of A, it takes the coordinates and applies pi to that. But if something is in the order, its image is in the order as well, because the thing is order preserving, and backwards as well. So the pi is actually a bijection between the subset of the square that is the order and it, to itself. And the members of the order are all symmetric because their coordinates are members of A. And so that's all fine. So this is hereditarily symmetric. So So this order is a member of a V, and that means that A doesn't have a well order in V, but it does have a linear order in V. The one that we gave it from the outside. And I think I mentioned this last week, but if you have a member of the ideal, then in this case, if I look at the subgroup of G, that of the members of the subgroup that fix all the elements of E, or I'm looking at the members of the subgroup that simply leave E invariant, normally certainly we have an inclusion from the left to the right. And if we were looking at arbitrary permutations, that was the best we could say. But now, E, if it's a member of I, is a finite set, and pi is order preserving. Pi is order preserving, so the minimum of E goes to the minimum of E. And so you walk along all the members of E, and you find that all the members of E stay in their place. So that means that if pi is in the symmetry group, it leaves all the members of E fixed. And this is a crucial point later in the proof of the properties of the model. The fact that the fix and the sim are the same helps at some point in the proof. Okay, so now what did I say last week? And I sort of sketched the whole thing, and I want to go through it once more so that we know that all the details are actually correct. So A has no well order. Every member of V has a linear order. And the linear order belongs to V, of course. Of course it has a linear order in the big universe. It even has a well order. But there is a linear order of that thing that is actually a member of the submodel. So that means that, and I talked about that last week, there is a fine line between asking, does everything have a linear order or does everything have a well order? asking if everything has a well order is a stronger question than does everything have a linear order. We get a model where every set has a linear order, and yet at least one set doesn't have a well order. So that ordering principle, everything has a linear order, is strictly weaker than the axiom of choice. And as I mentioned, that was a question of Franco that Mostowski answered with this model here. Yes?
I'm not sure if I forgot that you mentioned this last week, but is this linear order a global one, or?
That was the next remark that I was going to make. In fact, or that's the point. I was going to raise the point anyway, but thank you. If V, that was the big universe, that was the universe generated by all the atoms, if that happens to have a global well order, and having a global well order of the universe is formally but also strictly stronger than the axiom of choice, the well ordering theorem. Well ordering theorem says every individual set has its own individual well order. Global choice, global well order says you can well order the whole universe with one formula. Yeah.
These orders are proper clauses.
Yeah. Yeah. So if you like proper classes, then this means there is a proper class of pairs that well orders the whole universe. So if you take a subclass, then it also has, every subclass has the smallest element. You can also say there is a formula phi with two variables and maybe some parameters in it, that when I relativize it to any set whatsoever, it always yields a well order. And I'm stating this, then the question of course is, but is that actually consistent? Answer, yes. What Gödel did in the 1940s, when he proved the consistency of the axiom of choice and the generalized continuum hypothesis, what he actually constructed was a model with a definable global well ordering. Just a formula, relatively simple as in complexity terms, that would well order the whole universe. So this is a consistent assumption, and when you apply that consistent assumption to this situation, you will get a global linear order, so one formula that makes all the elements of V comparable in that order. So, how does that work? Well, it needs a technical result. I mentioned that last week, but I didn't have much time to actually go through the proof. And for a while now, we will simply leave set theory and we'll be doing algebra and permutations and such. Of course, we'll be doing set theory because we are permuting sets and points and everything, but the methods are just algebraic. And it's sort of surprising how much effort it would actually take to prove this. So we're going to do some okay, so technical fact. The technical fact that we need is this. Every member of the symmetric model V has a minimum support. And what was that? So what was the support again? Well, this. A member of the ideal such that the fixed subgroup for that member is part of the symmetry group of X. And for all the other supports, for all the supports of X, we know that E is a subset of that. So there is a minimum support for every member of the universe. Feel free to play with the blinds if the sun is threatening to kill you, vampires that you are. Anyway. So everything has a minimum support, and the question, where does that come from? Well, it comes from this. If you have two supports of X in our situation, this is not a general theorem about general permutation models. It's for this special model. If we have two supports and we intersect them, we get another support. And what is the proof? Well, the proof boils down to we take the subgroup generated by the two fixed subgroups for E1 and E2, and we show that it is exactly equal to this. Now, one inclusion is clear, because if something fixes all the members of E1, then it also fixes certainly all the members of the intersection. And the same for E2. That means this is a subset of that subgroup, and that means whatever it generates is still a subset of that subgroup. Fine. More difficult is the reverse. Because if you have something that fixes only the members of the intersection, how do you connect that to maps that fix members of E1 and E2? Now, I think I said this also last week, and if not, then this is new. I was reading this in Jech's book, and Jech says, well, draw a few pictures and you'll see, roughly. And I was drawing a few pictures and I didn't. So I went back to Mostowski's original paper, and I discovered that he took 2 or 3 pages to actually establish this. Well, he was very careful, but nevertheless, it took a bit more effort than just draw a few pictures to get this done. And here's how it goes. Like I said, the proof is just fiddling around with group elements. The first case is when the intersection of E1 and E2 is empty, because then we need to show that we get the whole group when we take this generating business. Because the fixed subgroup for the empty set is the whole group. And believe it or not, that is actually easy. Well, easier than the general case. And let me put it that way. Okay, let's call this group H, so that we don't have to write that whole thing anymore. Here's the first step, and now it says, look at my notes of last week. Okay, here we go. Here's the situation. We have an A and a B, and no loss of generality. A is less than B. And we want to move A to B. How? Well, you could say without moving any of the elements of E1 and E2. And if you're lucky, you can do that. But let's look at this number, the number of points in the union, oops, that should be E. Look at the number of points in the union of E1 and E2 that are between, could possibly be inclusive, A and B. Well, if n is equal to 0, then there is no problem. all the points of the union, E1 and E2, are outside the closed interval. So possibly there is a maximum point here that could, there need not be any points. So this would then be sort of an ideal point at the beginning of the set. I don't really care. And there's a minimum here. Now, what do we know about this interval here? It's isomorphic to the rationals. Because it's an open interval in the rationals, therefore it's isomorphic to the rationals. There is an isomorphism of this interval only that moves A to B. And we simply extend this by the identity on this and on that. And so then pi belongs to H because it fixes everything. And done. But this was really the easy case because I said no problem. I want to sort of recycle this a bit. Now, E1 and E2 are finite. Okay? So that means that of all the things outside this closed interval, again, there is a minimum. But I'm taking I'm using again that I'm working with the rationals. I take the smallest thing above B and I take something in between. That's what I call D. I take the maximum below A and take something in between and I call that C. So the number of elements in AB intersect the union is the same as the number of elements in CD intersect the union. Because I just make the interval a little bit big. And I'm going to play only in the interval from C to D. So what I'm going to do is I create a pi, and it's going to be the identity here, fine. So it leaves a few points invariant. It's going to be the identity here, fine. But here, it's going to be a composition. What composition? Well, assume n is equal to 1. I'll show you how to handle one point. If there is one point in the union, in the intersection, then we already need two permutations to do whatever it is that we want to do. We're going to. I'm going to show you how to move A to the right. And actually, in most of the cases, we need only one permutation. there is a map. Sorry. If A belongs to E1, and it happens, so this is the only point in the union that is between A and B. Then I have an automorphism that maps A just to the right a little bit. Okay? That pi keeps all the members of E2 fixed, because the members of E2 are outside the interval CD. So pi is in our group H. And we're in case n equals 0. Okay? If I am in case 2, I can find something in fix E1 that does the trick. If I'm in case 3, I get a pi in E2 that moves B down a little bit. If I'm in case 4, then again I move B down a little bit, and every time I get back to case n equals 0. So what do I do if A and B are not in the union? So in that case, I have a point E, let's say it is in E1. We take a permutation, an order-preserving map that lets A jump over E. That map definitely moves E as well, because E is over here, so its image will be over here somewhere. And that's fine. It's not in any of the EU, EE1 or E2. It's been moved. And all I know is that I have a permutation that is in H that moves A a little bit. And again, we're in the case n equals 0. Now, I didn't really use that the case was, okay, here I kind of used that it was the case n equal 1. But I could consider this to be the case k plus 1, and I let E be the smallest member of the union that is just above A. It could be A, or it could be a little bit bigger than A. Either way, I get a pi in the fix that moves E of A of itself, and it makes it jump that thing E. And it brings me to the case K. Then I make another jump, and I make another jump, and every time, okay, then in that particular case, I want to make sure that all the other points in the union stay where they are. So let me draw that picture a little bit close, a little bit larger. So E could possibly be A. I don't really care. And here, and here is the next element of that intersection. And then all I do is I say that I want A to jump E, but I want the whole map to be the identity here as well. And that's no problem because all the intervals in that linear order are isomorphic to the rational, so I can do whatever the hell I want inside an interval, as long as I keep the endpoints fixed. So I make one jump, and if E is in E1, this is in the fix of E2. If E is in E2, this is in the fix of E1. And now you see what's going to happen. I'm going to get a product of members of fix E1, fix E2, fix E1, fix E2, fix E1, fix E2, or some combination thereof that keeps moving A to the left. Sorry, to the right. My left, your right. And after a while, we have moved it to B. Okay? Now, that's a far cry from saying that we have generated the whole G. Okay, let's. Okay, this is going to take a bit more time than I thought, but never mind. I'll do the global case first, and then we'll have a short break. Suppose we have two finite sets, rather than just 2 points. Suppose you have two finite sets that are all in the same order, indexed. Then you can find a pi in H that moves the whole finite set of A's to the finite set of B's in an order-preserving fashion. Really? Yes. By induction on n. We have the case n equal 1. And if we go from n to n plus 1, we simply take a map from H that moves the first members to the first member. So if we have n plus 1 here and n plus 1 there, we apply the inductive assumption by moving the first n members to their correct place. And then we will be able to move an to bn without moving any of the other points, if we do that in the right way. You can also move one point first and then do the other stuff. Okay, but this simply will be induction. And okay, if you're a bit shall we say, you can move these points around a lot. So you can create lots of room to move before you actually do it. So the very first thing that you might want to try doesn't quite work, because when you move the last point over some points from the ones given, that's a bit of a problem. But you can do something like this. Okay, I'll indicate this. Suppose you were going to do this. Now, the inductive assumption says we can move A0 up to an minus 1 to the corresponding b's. So this one goes there. And so the an goes there. Okay, no, this is okay, this is fine. And all I need to do is move an to bn. And I can do that without disturbing anything that I did before, because the way the proof went, I could find members of H that were working in very small intervals. As long as I stay the identity outside big intervals, that was even better. So now we know how to move the points that we finitely many points, but we still didn't take care of any arbitrary order-preserving map from A to itself. Well, we have our map pi, and it maps E1 to something and E2 to something. How do we relate this to those fixed mappings? Well, we take step 2 and apply it to the union of E1 and E2, at least to the union of their images. And that's the A's, and what are the B's? The B's are the original points. I have an order isomorphism that maps E1 union E2 to something. Well, now I have two finite sets of the same cardinality that have a specific order. Step 2 says I can make something in H that maps this back to that. Ooh. But rho times pi is the identity on E1 and E2. So it's definitely in the group H. Oh, but then rho inverse times rho times pi is in H as well. Oh, wait a minute, that means pi is in H. So there. So lots of effort was spent in showing how to move finite sets of points around using maps that either fixed E or fixed E1 or fixed E2. But once we had that, we could suddenly show that we could create all the order preserving maps that we wanted by this clever trick. And this is not mine, this is Mostowski's trick. So credit to him. Arbitrary map. Look at its effect on these two finite sets. Oh, we can do something with members of the group H. Done. Okay, I'll finish this after the break. Sit. Well, apparently the coffee machine doesn't give coffee, but it does give hot water. So you can have some tea.